I also would like to welcome all of you here in Ostrava and also you online. This tutorial is the second tutorial of our IO-SEA project. It is organized under the umbrella of IT for Innovations National Supercomputing Center in Czech Republic. I'm really glad that I can welcome here today our three tutors. We have two tutors here in Ostrava, David Vasiliauskas and Ganeshan Unanishan. And we have one tutor online, say Nerissa Murthy. So, and the program will be following. Today, we will start with introduction of our IO-SEA project and CORTX introduction, which will be done by Sai. And then we will have a short walkthrough through CORTX GitHub. And after the coffee break, we will focus on setting up CORTX. We will have a demo sample and CORTX Motr on ephemeral services. More details we will see. And after the lunch break, we will have a hands-on workshop. Okay, so this is the short introduction, and now we will start with the introduction of IO-SEA project, which will be done by Sai and Nerissa Murthy. He is he leads European research and development for Seagate systems, focusing on next generation storage systems technologies. Sai has led and contributed to various Horizon2020 projects, such as SAJ2, IO-SEA, and Mastro, working with consortia on upcoming storage systems suitable for extreme scale HPC and next generation cloud computing. Sai also contributes to technology strategy in Europe by working with the ETP for HPC organization, where he sits on the board and contributes to the European strategic research agenda in the area of storage and IO, and also participates and contributes to the Gaia-X initiative in the area of storage. Before Seagate, Sai was involved as co-founder in a venture backend startup in California, working on internet-based storage area networking. Sai holds a PhD in the area of storage from Arizona State University.
In this introduction, I'll just cover the overall IO-SEA project, and it also helps to set the context for all the storage and IO problems that we see in as we get towards exascale supercomputing. So that's the main goal for this. So introduction for the IO-SEA, as part of the introduction, so I would like to introduce all the team that's working on the IO-SEA project, and CEA from France is the project coordinator, and so IT4I and Seagate who are here today. We are one of the partners in the consortium, and there's a total of 6 countries who are engaged in this nice exascale IO initiative. So what is IO-SEA? So IO-SEA is actually part of this SEA projects. So the idea is to try to build this modular supercomputing system sometime in the next few years. So in a modular supercomputing system, each of these boxes that you see can be scaled independently. So you have in this supercomputing system, you have a bunch of cluster nodes, which are standard CPU cores. Then you have booster nodes, which could be your accelerators. And there's a data analytics module and a neuromorphic module, a quantum module, and also a multi-tiered storage system. So they can all elastically be shrinked and increased and decreased based on the types of supercomputing applications that you have. And we believe this is a very good way of building supercomputers, specifically at scale. So the 3C projects, so the Deep C project focuses on the software stack. uh, for for Exascale based on these heterogeneous systems. So you have the clusters and the boosters and the analytics. And the Red Sea works on the interconnection between all these different modules, looking at next generation interconnect. And this is where we sit in. So the IO-SEA project focuses specifically on the multi-tiered storage system that can support this kind of a modular supercomputing architecture. And the three projects, Deep Sea, IO-SEA, Red Sea, we all work very closely together to help to achieve this kind of a vision. And just a note that the three projects are funded by the EuroHPC 2019 call. So IO-SEA, the goal is to tackle these IO challenges as we head towards Exascale. So what are the main challenges that we see for Exascale supercomputing going forward? First is data scalability. So there's a massive increase in the amount of data stored and also the metadata. So if you actually look back at simulations in the past, it used to be heavily compute intensive, where you start the you just load some initial conditions, you do the simulation, you finish your simulation, and then you do some checkpointing. So it was not specifically very data intensive. So, but things have changed now. So supercomputing, and as you get towards Exascale, things are going to be very, very data intensive. There's going to be needs for loading data sets from external data sets. And the simulations are going to generate lots and lots of data that needs to be checkpointed. You need to store all the state, you need to store all the data sets, and then you need to do analytics on top of the data. You need to run some AI actions. So things are becoming very data intensive. Then the other trend for storage and IO, as you get towards Exascale, is that the number of clients, so system is scaling enormously. So number of clients that work on the storage system is increasing tremendously. And what this is happening, this is because of the multi-core and the many core and this kind of trends. And what's happening is that the performance gap between storage and computing, it's increasing and increasing. So storage speeds and feeds are also increasing, but the scale at which the compute is increasing is quite tremendous. So we continuously see this gap increasing. So that's the reason you have to start to really build smart storage systems as you get towards Exascale. And this is really the need of the hour. Then the other trend that we see is this evolution in heterogeneous computing with GPUs and also FPGAs and data processing units and all these kind of things. So when all these different technologies take over, then what's going to happen is that the OS will have very less available memory. So that's going to pose more and more of a challenge, which means that the IO system needs to step up to deal with the data deluge. And the other challenge that we have is data placement. So where do you move the data, to what time, to what location in memory, and based on the workflows and the application. So just by having these humongous data sets, so just managing all these data movements in the stack is going to be an extreme challenge. And of course, the last point is data heterogeneity. So this data is going to come from different sources. So it's going to be simulation data, external data sets, and then the output data that's going to be consumed by consumers possibly. So data is going to be quite heterogeneous, coming from various possible sources. So be it like satellites or IoT and things like that. So the current storage systems are not really designed for massive scale. So if you look at all the evolution of things like parallel file systems and things that we have, it actually is designed in a different age, when the assumptions of these systems were very different. The assumptions of core counts and the assumptions of what kind of interconnects you had and what kind of storage technologies you had was very different. especially when you look back to the history of file systems like Lustre. So these things have changed dramatically, and hence there is a need to build these new kind of storage systems, and IO-SEA embarks on that kind of a challenge. So within the IO-SEA project, so we are looking at a innovative software stack which uses object stores. So we are not using a parallel file system. So we are using an object storage system. So I'll explain a bit more as I go along what is this object storage system. And then you have a hierarchical storage management system to actually work with different tiers of storage technologies. You have not just the hard drive tier, but you have SSD tier and NVMe tier and also tapes. So there is a need to work with data across all these different tiers. So that's why you have the HSM system. And then the other concept that we have introduced is a so-called on-demand ephemeral provisioning of services. So when you have this object storage system, data can be consumed in various ways from the object storage system. It could be through a S3 protocol, it could be through NFS protocol, or it could be through any other protocol. So all these protocols can be spawned on demand based on the needs of the use cases. So that's what we mean by on-demand ephemeral provisioning. And then you have this IO instrumentation. So with such a large system, you have so many nodes, the stack is so complex, you have petabytes and petabytes of storage. So how do you actually analyze what's going on in your system and what's happening to the applications? How can you holistically view in one pane of glass, so to speak, what's happening in the entire system? So that's the reason you have this intelligent telemetry analytics, where you collect telemetry data from these different points in the stack and you subject them through smart AI-based analytics, which helps you to identify hotspots and also what's going on in the application. So the last but not the least is the entire stack, the IO-SEA stack, is co-designed with the next generation of IO-intensive applications. So I'll mention a bit in the end what these kind of applications are. And last but not the least, we have also developed a very new interface to be used by the applications, which more closely connects the applications to the storage infrastructure, which is a semantically aware interface. So where the applications can actually specify semantics behind what's being stored. That's called the data DASI interface. And then big picture of the IO-SEA architecture. So here we have the compute nodes at the top. Then you have the DASI interface that is used by the application. And then you have all these ephemeral services that are spawned on demand in so-called data nodes. So data nodes is kind of it's kind of like your burst buffers, but it's a lot more flexible and a lot more complex in the sense that you have these different kind of services working with data in very high speed devices like NVMe and SSDs. And on the back you have the CORTX Motr object storage, which we are going to talk about today in a lot of depth. So the CORTX Motr object storage is built to work with different kind of storage tiers, including NVMe SSD, high performance SSD, and archive HDD. And on the back, you have the HSM system also working with tapes through this intelligent software layer called Phobos. So it's interesting in the project that we are bringing in tape into the fold as part of the stack as well. So even data in the tape is visible as objects. So it's quite interesting. So IO-SEA, we leverage software from various open source communities and from the partners. We've shown the big list here. Some of you might obviously be involved in some of these initiatives. So the software is developed using two different infrastructures. One is the IT4I infrastructure, which is offering a cluster of VMs used for software development and testing. And the other is the deep test cluster at Jülich Supercomputing Center, where we will be integrating all the pieces of the software. And this project leverages one of the old prototypes that we have from the Sage 2 project. It's called the Sage project, Sage prototype. I'll tell you a little bit about that in a bit. And that's being refurbished as the new IO-SEA prototype, and we are going to be using that as well. The deep test cluster demonstrates the modular supercomputing architecture. And this is for the ephemeral data access environment. You have these specialized data nodes will be leveraged, and I think I've mentioned this already. So this is an example of these ephemeral IO services. So essentially, you have the clients is the compute nodes is where you're running the applications, which have all these clients like the smart bus buffer and the NFS and the S3 clients. So and then the DASI client, and also could be like existing parallel file systems. So the ephemeral IO services essentially will consist of all these gateways like the smart bus buffer, NFS server, S3 server, and the DASI gateway, etc. So the data nodes also run the CORTX Motr object storage server, which is going to present all the data in the NVMe and the SSDs. And on the back end, you have the long-term storage, where the different tiers of storage are going to be managed by the CORTX Motr servers, and the tape libraries managed by Phobos. So the implication of this is that you have these concepts of data sets and namespaces. So you could have, for example, a data set is stored as one S3 bucket, and the files could be stored as S3 objects. And all these namespaces, which shows how all these data sets are related. So they could be stored in different metadata objects. So this is the beauty of having object storage at the very foundation of this kind of systems, is you could overlay any kind of structure to the data, however you please. And so for the HSM, it's about getting the right data at the right place at the right time. So essentially you have the NVMe SSD tiers in the data nodes, and all these 4 different tiers in the backend storage and the tapes. So so the entire the HSM, there's a new HSM API that's being designed. It's called the Hestia HSM API. So Hestia HSM API, it's a low-level API, C++ API to manage data placement between the different tiers, and is usable on a Motr client data node. And the other interface is an S3 server that can work with this Hestia API and provides a higher level kind of interfacing, and like things like namespace management, user authentication. So authentication, all that is done in the S3 server at the top. So this is a quick introduction to DASI. It's the data access and storage interfaces. This will be built to abstract abstract out the complex storage layers, and you have semantic description of data, and you can actually describe data in a manner that is more that the scientific domain experts are more conversant with. So this is just an example of how you can describe semantic information as part of your data. So I'll just skip this one, and then you have the instrumentation and monitoring system, which where you get a feel for what's happening throughout the system. So you gather the knowledge of IO behavior and the knowledge will feed the algorithms that will allocate all these IO services and the data nodes, resources within these data nodes. Also, gathering all this knowledge will enable you to make very efficient scheduling decisions as well. And AI algorithms will complement scheduling decisions made by users. So at the moment, it's typically users that make these decisions, but we aim to have a complement of the AI algorithms. And also the IO and instrumentation tools will also be adapted for each of these different kind of ephemeral services that we have. So on the right, you have just a quick overview of the different kinds of individual components that you have as part of your monitoring infrastructure. So we have a central monitoring engine which collects data from an application perspective, like and the processes like LLView, and you have the parastation, the health checker, infrastructure health checker, and also telemetry, for example, coming from the CORTX Motr, called where we show it as the telemetry framework. And also like different components of IO software that's producing the instrumentation. So just a quick note that the IO-SEA project, we are also very closely collaborating with the other C projects, which I also already mentioned, but also the other EuroHPC projects as well. So IO-SEA is the one of the IO projects, and Admire is the other IO project. So which are so-called IO-SEA IO flagships in EuroHPC. And with Admire, we are in the process of collecting all these IO traces in HPC. So the plan is for the IO-SEA software stack will be used in the next EuroHPC Exascale pilot. It's called the UPEX pilot. So we are already on track for using all these different storage technologies as part of the Exascale pilots. So what have we done until now? So we have the workflow, data nodes, and ephemeral services. They are available on the IT4I infrastructure. And the different monitoring tools, they're integrated and they have been deployed on the deep cluster. And the HSM API, HTI, is now available, and HTI integrates with HSM in object stores. And the first version of the DASI interface has been delivered. And the first version of the ephemeral services are also ready to be spawned by workflows. And we are ready for benchmarking on the deep cluster in the second half of the project. So we just had a month 18 halfway review just a couple of weeks ago. So we are in the second phase of the project, and everything will finally be validated by the use cases. And this is a quick peek at the kinds of applications. I won't go into detail, but this is just to give you a feel for what we have. We have applications from particle physics, from astrophysics, and terrestrial systems modeling, and weather forecasting, electron microscopy imaging, and these are all very data intensive applications. So yeah, so this is a quick overview of IO-SEA, and also I hopefully laid the context for the exascale IO problems that we try to solve in the project. And the focus of today obviously is going to be the object storage software piece that drives this entire IO stack. So yeah, that's mainly it for this piece of the talk. So there's a second piece which covers CORTX Motr in a bit more detail. So so Karina and Katrina, should I take some questions now, or should I go to the next piece and take questions in the end? What do you think?
If anybody has a question, then
yeah, I can take some questions now, and then I can get to the second part of the talk. Hopefully, I'm following the time. Yeah, I'm keeping up with the time as best as I can. So feel free to drop the questions in the in the chat as well. Even even if some question comes to your mind at a later point, please let me know. So I'll keep going in that case in the interest of time. So let me get my other presentation up. Give me just a second. So I share my screen. And can I do a quick check again if my audio was clear? Hopefully there was no problems with the connection.
We can hear you.
Okay, perfect. Thank you. Right. Let me do this one. Just 1 second. Yeah, I've got this one. Okay. Screen. So this is the second part of the introduction, where we introduce to you a little bit about the CORTX Motr object storage system that we use in the IO-SEA project. And I would like to provide a bit of background on the CORTX Motr object storage software itself, and provide you a brief architectural summary of CORTX Motr. So the main goal of CORTX Motr, so just to give you a quick sort of a background on this. So in the last few years, we saw these different changes happening. So one was we realized that in extreme scale computing, the IO needs were changing very quickly, and the storage and compute gap was increasing. With all the heterogeneity, multi-core, many-core on the compute side, and the HDDs, speeds and feeds, which could not keep up. Even though the HDD densities are increasing and there are new storage technologies like NVM, NVRAM, NVMe protocols, etc. But the speeds and feeds we need to try to keep up. And then the other trend that we saw is for the big data analysis, we had to avoid data movements between the compute and storage as much as possible. And for big data analysis workflows, you manage and process extremely large data sets where they are. So we started seeing big data analysis creeping into the extreme scale computing infrastructures like in 2014, 2015. Kind of a time frame, which was during the start of the SAGE project, which I'm going to tell you a bit about. And then now we have the AI and the deep learning aspects coming into the pipeline of scientific computing, where you have very large memory requirements, and the storage and IO requirements are something that we are continuing to learn. We are still not experts at handling this, but we continue to learn how to build storage for this. So the idea was the decision was to build a storage system that could accommodate all these different kinds of workflows in a same as part of the same infrastructure. So typically what happens is for supercomputers, for HPC, you build different storage system. And for big data analysis, you build a different storage system based on Hadoop and MapReduce and these kind of things. And for extreme scale computing, it's parallel file system. So AI and DL is sort of it's more memory intensive. So the idea is to have object storage drive this kind of infrastructure. So if you have object storage as a foundational layer, you will be able to accommodate all these different kinds of elements using your same infrastructure. So that was the goal of having that was the goal for also starting to design CORTX Motr for HPC. And CORTX Motr has been used in SAGE and SAGE 2 project. I'll very quickly just provide a context of what was done during those projects, because they are natural precursors to the IO-SEA project as well. So the SAGE project lasted from 2015 to 2018, and we built this 2 racks of storage tiers, which we had this NVRAM tier called SAGE tier 1. We have the SSD tier, SAGE tier 2, HDD high-speed HDD tier 3, and the archival grade tier 4. And we had some local clients running the CORTX Motr API, which we used to call Clovis during those days. So this storage system was based on CORTX Motr and was installed at EuroHPC Supercomputing Center in Germany. And we co-designed the system with this big data application. So 2015 was when you had big data applications, big data aspects in the workflow. So AI and deep learning was not so much, hadn't percolated into this yet so much. So we assembled it in Seagate and deployed it in EuroHPC. And we also ported some of all these big data extreme computing applications, and also ported the various stack components. So for CORTX Motr, which we call as object store, so we made the CORTX Motr was made to work with these different tiers like NVDIM, 3D Crosspoint, NAND Flash, etc. And the CORTX Motr API was called the Clovis API. And the idea was that these different use cases, programming models, and the tools and the applications would use the object storage system. And we also built in this so-called in-storage computing capabilities within the object store, so that the applications could ship in some functions and run it close to the storage from the compute system. And CORTX Motr, so we just started off the project as part of SAGE. And we built these basic foundational elements, like things like so-called layouts, which is working with these different tiers of storage, and containers where you group objects into buckets, and porting for 3D Crosspoint, etc., and function shipping, and usage of the CORTX Motr API. So these were for the first time we did it as part of the SAGE project. And also we integrated it with some runtimes, and we used some big data analysis applications like Apache Flink as part of the stack. And we also explored how you can actually bypass IO paradigms like MPI-IO, how you can overcome some of the problems of that. And we also integrated the system with the performance analysis tools and things like that. So with stage 2, we continued the CORTX Motr journey. This is our team that was involved in the stage 2 project. So from 2018 to 2021. And most of these, as you see, a big part of the partners, we continue in the IO-SEA project as well. So with stage 2 for CORTX Motr, the vision was to extend the storage system into the compute nodes and blur the lines between memory and storage. And 4 primary innovations for stage 2 was to have to deal with compute node local memories as well as part of the software stack, especially the NVRAM. And we also explored byte addressable extensions into persistent storage, which we call the global memory abstraction, where you can actually map your storage in persistent tiers directly into memory and work with those objects. And we co-designed the CORTX Motr-based system with these new workflows from AI and deep learning. And we also co-designed with ARM-based environments as well. So we added an ARM tier to the stack. So let me just skip this. So this just shows that the object storage CORTX Motr was right in the middle of the stack, where you had this use cases and workflows at the very top, and the ARM compute and the x86 as well, tiers at the bottom, and everything was managed by the CORTX Motr object storage system. And we also had explored in Sage 2 along with CORTX Motr new concepts such as transaction management and quality of service, is to smartly work with the different tiers based on what kind of quality of service is needed by the users. So we worked on these kind of paradigms, and at the very top, we had like tools such as TensorFlow from the AI community integrate with the CORTX Motr API. So we explored some of that for the first time. So this is the kind of use cases in Sage 2 that we used. So at the end of Sage 2, after Sage and Sage 2, this is the system that we achieved. So initially you saw those 2 racks, and now we extended it to 3 racks. So where you had all the tiers, the NVRAM tier, tier 1, tier 2, SSD tiers, tier 3 and 4, the HDD tiers. But we also had these ARM nodes as well, which are running ARM Thunder X2 nodes, which are also running CORTX Motr by them. And you had these various different types of clients like the data warp and the visualization nodes. So on rack 3, where we used to locally run some workloads and the client. So all this was at Jülich Supercomputing Center. So we demonstrated applications, all these applications running on these 3 racks. And we continued. So during the time frame of Sage 2, we decided to fully open source CORTX Motr. So initially, CORTX Motr was an internal project within Seagate. It was not open source, but now it's a open source project available for the community, and it's in Apache V2. So very flexible license. So anyone can actually work on the code base and edit it and fork it and things like that. So it's the same prototype that we use in the IO-SEA project as well, the CORTX Motr based system. So for Sage 2, so I just show some of these things that were achieved as part of the CORTX Motr system. So I discussed some of this in the previous slide. So I skip this, and the work that were done in Sage and Sage 2 ultimately helped in the further build out of CORTX Motr and helped to enable it to be an open source project. So which my colleague David will briefly tell you about the GitHub in the next talk. So then I changed gears a little bit and then talk about the CORTX Motr architecture. Just provide you a quick overview. So this shows essentially continuing from Sage and Sage 2 how CORTX Motr has been used in IO-SEA. So it's running the services, the various services like the ephemeral services. They are running on the data nodes. So the CORTX Motr servers run on the data nodes. Also potentially also some clients can also run here on the data nodes. And the CORTX Motr servers expose all the data in the NVMe and NVRAM tiers. And the CORTX Motr servers also reside on the backend storage, exposing all these different externals, SSDs and HDDs. And on the backend, CORTX Motr also works with the Phobos software that exposes the data on the tape as objects. So then coming to CORTX Motr, I'll provide you a quick overview of the different components of CORTX Motr. So CORTX Motr is essentially it's a core component of a new cloud software stack which was initially developed by Seagate, and it's now fully open source project. So it has a client interface through which, and CORTX Motr has an object store where you can store objects, as well as key value store that helps you to define the relations between these objects. And the stack consists of this access interface and an extension interface. Access interface is used to directly access and work with the objects and the key value stores. And the extension interface is where you build your own third-party plugins on top of the interface, such as things like archiving, indexing, backup, migration. So those could all be extensions that you build on top of the CORTX Motr. And the access interface you can access, so one thing to bear in mind is that the CORTX Motr system is very low level. You can't directly use it. It's like you have to overlay some gateways on top of the CORTX Motr API. So it's built to be very low level system. So you could have things like S3 built on top of CORTX Motr. You can have like HDF5, or you can have PNFS or POSIX. So you can build all these layers on top of CORTX Motr. So that's how you actually access data in CORTX Motr. And CORTX Motr is the layer that fundamentally works with the storage system and provides all the resiliency, semantics, and things like that, performance. So we have similar products like Ceph and Scality and all this kind of things, but there are some differentiations with what was done in CORTX Motr. So how is CORTX Motr different architecturally? Is horizontally scalable. So you can grow the system by adding more number of nodes very easily, so that there are no specific hotspots. And you can also scale it vertically for individual nodes. You can add more memory and more processors. And the system is built to be very fault tolerant. So we have very flexible erasure coding that can take care of the failures. So you can specify the different kinds of erasure coding, like the number of messages and parity and things like that, and they're all distributed. And CORTX Motr architecturally, there's also built-in monitoring. So you can systematically collect all the telemetry data from the different points in the stack, and you don't have to rely on log messages like Lustre, and you can scale up and scale down this telemetry information as needed. And the extension interface is also very flexible, where you can build your third-party applications. And it's also very powerful and portable because it runs in user space and potentially could work on any version of Linux. So just an example of how something is overlaid on top of CORTX Motr. I was saying that it's a very low-level API. So libmotor is the low-level API that works with the different objects. On the left is the CORTX Motr objects using the data on these different boxes. So we have IO services that exposes CORTX Motr objects. And on the right side, you have the data indexing service, the DIX service, where you work with the key value pairs that are also sitting on these different devices. So libmotor essentially exposes these very low-level objects and key value pairs. But at the top, you have, for example, I show an example of an S3 server, where an S3 client issues like the gets and the puts, etc. And at the S3 layer is where you define your buckets and users and the access control lists and attributes, etc. And you have the concept of an S3 object that is then mapped to a CORTX Motr object. And all these attributes, you map them to key value pairs. So this is a very top level overview of how things are potentially overlaid on top of a low level object store. Very similarly, you have this parallel file systems or NFS. So how that is overlaid on top of a low level object store is you have files that are mapped to objects, and then you have all these directories and permissions that are mapped to key value pairs. So essentially, everything works with the libmotor API. And also, we were thinking about having interoperability between S3 and NFS. So even if you have data in S3 buckets, you should be able to view them through NFS, through some common metadata formats. So that was also something that was a work in progress. So an object is just an array of blocks. So it can be in different enclosures, which could be in different racks. So you have FIDs here, you have these different objects which are shown in different colors. You have the data bits and the parity bits just below this data. So this just gives you an example of how these different units of the objects and the parity, they are distributed across your entire infrastructure, and gives you this very powerful resiliency and reliability. So you can have any kind of so-called parity declustered RAID, where you have any number of n, which is the number of data blocks, and the k, the parity blocks, and some spare units. So they're all n, k and s can be dynamically adjusted based on what is needed. And you can also have other kinds of layouts as well, such as like deduplicated layouts and things like that, and composite layouts across multiple tiers. So that's how an object is laid out across various enclosures and racks. And similarly, for the indexing layout, you have the distributed index that are actually divided and mapped into different nodes. So exactly like your object layout. So even you have a layout for the index as well. So this also just shows you another overview of what happens if you have an S3 server running over CORTX Motr API. So you, for example, when you write an object at a S3 layer, and which consists of three units, 0, 1, and 2. So essentially, they are all directed to different IO services, and there's also a parity that's also sent to a different IO service, and that's how you break it down. So CORTX Motr, it also has is a metadata backend, which is internally used by CORTX Motr itself for storing object identifiers and housekeeping, like free blocks and all this kind of configuration data. But the same metadata backend can also be used by external applications for storing things like NFS directories and S3 directories and all these attributes, things like that. So all the metadata is managed by this B backend. Yeah, it's memory oriented. It could be in memory. It's designed to be fast transactional engine. You use B trees as the main indexing mechanism there. So it's all since all these transactions can be in memory transactions, you can use for the backend some very fast storage tiers like NVRAM or NVMe. And these are all the examples of third-party applications that could be built on top of the extension interface, like things like encryption, compression. These are some examples, third-party applications that could be built on top of it. And so in the IO-SEA, I was mentioning that the different software components produce different telemetry records. And similarly, CORTX Motr also produces its own telemetry. It's called Analytics and Diagnostics Database, or ADDB. And why is it very relevant is because systems are growing larger and more complex, and you need to understand what's happening to how you can diagnose failures and faults. So all this very, very large amounts of telemetry data can be collected very systematically, and you can kind of get a feel for what's going on in your infrastructure. So this is just an example of, so ADDB has a certain payload. So as you see, it's a very structured telemetry records. You should be able to put this in this database and do some analysis on it. So it's just an example of how ADDB, the analytics and diagnostics have been used for doing these different kinds of analytics within the system. Even things like IO path analysis and things like that. So yeah, so we could also collect all these telemetry records and also feed it into a simulator potentially to answer questions of what if, of what may happen if something changes to the infrastructure. So there are lots of possibilities when you collect these structured telemetry records. So yeah, so this is a very like a very quick overview of CORTX Motr as an object store. Hopefully this has given a feel for you about how these object storage systems are designed for like high performance computing oriented applications. So we use CORTX Motr because this is something we have been working for a long time. But actually, if you think about it, all the open source object stores like DEOS, for example, so they have a very similar stack as well. So if you look at some of, for example, the DEOS stack from Intel, it's also very similar in the sense that you have the low-level API and have gateways on top of it. So there is a lots that you can learn also looking at the other object stores as well. I mean, for anyone interested in this area of storage and IO, I would really encourage you to look at these other open source projects along with CORTX Motr and pick up the best elements from that.
So our next speaker will be Ganashan Umanashan. He works as a senior software engineer at Seagate Systems, focusing on next generation storage systems technology. Ganashan had led and contributed to many technical work packages in Horizon2020 projects such as SASH2, Maestro, and IO-SEA. Jonathan's interests are mostly in demonstrating the values and functionalities of Seagate's storage systems to their partners via EU projects. Okay, so the floor is yours.
Okay, so for this presentation, I'm going to take you through our GitHub site. So for all CORTX related activities, the main site is github.com Seagate CORTX. So if you search on Google, this is where you should land. So from here, this is the landing page, and here you can see all the components that are part of our CORTX development. First of all, if you want to know more about the overall CORTX, then there is this README that provides all the information that is needed. For example, here's the introduction. It is an open source project. If you want to see what the license is, you click on this Apache 2.0 license. It will give you more details on the license. If you go down, then there is this section, getting started. Here, if you want to know the glossary, you click on glossary, it will take you there. There's a quick start section, terms and conditions, components. For example, let's say you want to know more on the components, click on it. It will take you to the documentation about the CORTX components. So this is the main page. And then within this page, we have all the repositories that are associated with CORTX listed here. This listing is coming up with the activities on each of the repository. For example, as I mentioned earlier, CORTX Motr. Motr is our main engine that is storing and managing data. So you can access CORTX Motr by clicking here. So this was a particular commit of that CORTX Motr, but if you want to go to the main page, you can just click again here. That will take you to the Motr repository. This repository is also, again, self-contained. All the development activities are done here. You can go down and you will see there is a README. So for Motr, all the information that you need for developing or becoming a developer or compiling it for various other purposes can be found here. So this is Motr. Then let me go back. Let's go to another one. For example, the Kubernetes development. If you are interested in Kubernetes development, you will click here. It will take you to CORTX K8 main repository. Again, this is another self-contained repository. It's got introduction to documentation about the Kubernetes development. If you want to contribute to Kubernetes development, this is where you need to find the related documentation. If you are interested in this particular architecture, then here you have got details on the Kubernetes architecture for CORTX. Okay, I will not go through all the documentation on all of them. So I'm just going to introduce you to the important repositories. So we have seen CORTX Motr. The other important one is the HEA repository. So you will need Motr and HEA if you just want to have a cluster that has Motr running, then you will also need the HEA RPM. So if you are interested in contributing to HEA or more details on HEA, this is where you will find. So there is a user guide and how to configure HEA, and all the installation instructions are available from here. Okay. So once you have Motr and HEA, this allows you to build a simple cluster. So David is going to demonstrate a single node cluster today. So this cluster uses Motr and HEA. Once you have these two, you have a running cluster. What can you do with a running cluster? You can run some applications if you want. So there are some sample applications. This is CORTX Motr sample labs. Here you have, this itself is a repository, and it provides basically 3 applications: copy, cat, and remove. Copy basically takes a file and copy that as an object in Motr. Cat reads an object and then save it as a file, and the remove basically deletes the object. So this is very simple. You can just store data, retrieve it, and you can delete. A simple demonstration of how you can use CORTX Motr. If you want to know more about running this on a particular cluster, then there are sections here. For example, if you want to run this on our Sage platform, these are the commands. If you want to run it on a VM, single node VM, these are the commands. We will demonstrate some of them later. Okay, so that is for repositories. And then if you are interested in the S3 interface, that is the RGW repository. So here you will see the activities related to CORTX RGW. Again, this is a self-contained repository. You have all the required documentation available here. I will not go through this documentation, but I will just simply say that if you want to build Ceph RGW, or if you want to contribute, this is the place you should be looking at. Okay, I will go through one final repository. There are many repositories. For example, We have Halon, and then we also have some utils. We also have a RGW integration repository. So this is another one that if you want to have RGW running in many servers, then this is where you should look at. So again, this is self-contained, and you will have all the information needed from here. So that's basically the introduction to the CORTX repositories in Seagate GitHub.
So hi guys, my name is David. So it'll be a live demo. To some of you, I don't know if you saw some of the emails that were sent out. We did have a prep video out there. So to some of you who watched it, might have seen how to ahead of time prepare with CORTX on a machine that you have. But if not, we'll be doing this. We'll be doing this live. So I'm in my. So this is a machine I've set up just before we started this demo. So let me just show you. So if I just cat OS release, so it's Rocky Linux running 8.6. So that's the base image that's used. And if I check the kernel as well, it's uname, right? 4.18. So most of you will be starting from this page. It's the IO-SEA event page. So if you scroll down in one of the prerequisites, it's a link to the IO-SEA CORTX Motr VM. So you can navigate it through here or just simply go there yourself. So if we're to start off, we're simply going to clone this repo. And I should have Git on this machine. I do. So I'm going to say git clone. It's going to be the IO-SEA VM. So we've went ahead and cloned that. So we're going to cd into this and then just list the directory, right? So we can simply start away right away, actually. And if I cat the README, so it's README TXT file that we want to have a look at. And we can see one of the first few steps is we're going to actually set up the CORTX RPM repo. So here in this step, we fetch the RPMs and get them available on the system, right? So we'll do this live. So whoever wants to follow along with me can go ahead and do that, or if not, do it at a later time. Okay, so this takes a little bit of time. So the video I had put up was about 10 or 11 minutes in length. So it kind of skips over some of these 2-3 minute periods where it installs. It's not really interesting. It's just pulling packages down and installing. So you can see all the dependencies being pulled. We have CORTX here that we talked about before. Yeah, so we're going to go ahead and let this finish. Okay, so this step we've completed. So if we refer back to the README, so at this point, we know what the repos are. Next step is to install these 3 commands. So it's sudo yum install CORTX here. So this probably takes the most amount of time since it's pulling in the motor dependencies and the rest of here dependencies. The other subsequent steps take a little bit less time because they have the motor base ready. So as far as live demo goes, this is a live demo, right? We're going through the dependencies, all the packages being pulled. So whoever's following along and they face any issues or doesn't work on their local machine, yeah, come ask me at lunchtime. So just for the purpose of the demo, next step is going to be CORTX Motr and Motr Develop. Let's get that installed. Okay, final step is Rados Gateway. The next step is to configure libfabric for CORTX as well. So for this step, we have a handy script called libfabconfig.sh. And all we have to do is just double check the network interface that we have. So in the example, in the less readme txt, we have enp0s3. We want to change that. So we want to get this value from running IP A. And for us, it's eth0. So all I have to say is sudo sh libfabconfig tcp, and then I just say eth0. So we've completed that step. So again, I can refer back, and to some of you who might be using tmux, you can use tmux, split the window side by side, and then look at that this way. I'm just going as the simplest approach here. The next step is to create some scratch space. So these will be our disks that Motr is going to be using. So we have a script for that. It's simply disk.sh. So it generates this scratch files for us. So again, referring back to what we need. So the only other step that we need to do next is modify the single node.yaml file. Single node.yaml file defines the cluster configuration. In order to start Motr up, you have to define which devices are attached, and also what extensions like FDMI or any other features you want to add for your cluster configuration. So at the minute, if I look inside my, let me just set the number and relative, I can see there's some things to change, like the path to Seagate, localhost, right? So we're going to go and change that. So just for purposes, if I do a PWD, I can see my user. Who am I? I can see I'm the demo user on this machine. So all I'm going to say there is within single node. So if any of you are following, host name, localhost for now. Data iFace, let me just set this. We want to change this to reflect our network interface. So it's going to be ETH0. Okay, libfab, everything else, and we can see we have the path / Seagate. So we do want to change that. We do want to change to say that every single instance of Seagate is going to be replaced with the path demo, which is my user. So I'm going to change that ahead across this whole file. So you can see home where we had Seagate, we now have demo. And if I do a quick search where Seagate was, I no longer have this in my text editor. Okay. So that's done. So we should be good now. So going back to our command .txt, we can see now that single node YAML, we have changed that, and you can see that in the README. And all we have to do now is run the HCTL bootstrap. HCTL bootstrap is the here. So that's the package that we mentioned earlier, which helps manage CORTX Motr. So I'm going to say sudo HCTL bootstrap. And it's going to be the single node YAML that we created. So at this point, we've made very small modifications to that configuration YAML script, and now we're setting up CORTX Motr. So you can see in the logs, we start the console server, wait for leader election. Obviously, for now, we're running single node, so there's nothing complicated happening here. Okay, so we should have this step. So our Motr services with here should be running. So everybody who's following along, if you've reached this point, you know that your single node without an S3 server is good to go. So in the README, next step, we probably just want to shut this instance down. And this does take a little bit of time. So we'll let that go ahead. And while that's doing that, I'd like to take the chance, I suppose, for now, and maybe see if there's any questions from any of the audience online or anybody here who has questions about setting up or the GitHub presentation that Ganeshan gave earlier on. that anybody would like to ask questions. Okay, so I guess we have nothing yet.
Sorry, could I ask a question?
Mm-hmm.
Yeah. So getting to this stage where I do HCTL start, just downloading one of the recommended VMs, plugging in the commands that are in the instructions, I get at starting motor phase 1 M0D, I consistently get a job for M0D at hexadecimal, I think, service failed because the fatal signal was delivered to the control process. Now, if I think if I check HCTL status on that, it's still, oh no, it says it's not running, but then if I try to start it, it will say that it is already running.
Probably try and kill it with, I'm not sure what environment you're running or what setup you have, but probably try and just kill it from the command line. If you look at your processes, like
Okay.
we'll check your processes and then try and kill it.
Okay, but this consistently happens across restarts and 2 separate VMs that I've set up according to the instructions that you published.
Okay, well, that's something I could have a look at that with you later. So you can reach me by email later on if something something you want to have a look at. Actually, while we're here, if we run into, say, for example, either you're stopping an instance, it takes a little bit of time, or something else. I think, Ganesh, you have a handy dandy command to get that killed off, right? Yeah. Do you want to? What is that? What is that command that we want to maybe share and show with the audience? No, I don't have it. Just off the top of your head, do you have it? Yeah, pkill M0D. Yeah, that's it. Yeah. So for those of you who are seeing any issues once you've started, you can always do this. So I wanted to show some of you that, look, if you get into a funny state or something's not stopping, something's not started, you can run these commands and yeah, get back to where you need to be. Right. Okay. So from this point on, we have the disk set up and we have HCTL. So the next interesting part is the S3 interface. So if you've got to that point, you verify that single node can work okay. You verify that you can start it up and HCTL clusters running. The next step in the instruction is just the S3 interface. So all you have to do there, like we have AWS CLI v3, just run this command. So this will pull all of the dependencies for AWS CLI. So same way that you would be working with on AWS or any other place, you can use this utility to interact with that S3 resource, right? And then just going back again, all we're going to run is this AWS CLI config. So for the purpose of running commands like AWS CLI, every time you run it, it looks inside your home directory to make sure you have the correct credentials. So for example, if I run this, it'll set up those credentials and they're located on your home user. So if I do very quickly, less.txt, the final step is to get the S3 interface up and running. So sorry if I was going through a little bit quickly through that. Last step, after you install your AWS CLI, configure your AWS CLI, and then run ceph4gw shell command. Yep. I see. The last line is a little bit cut off. Okay, let me see if I can fix that. If I change to this, was that a little bit better? Yeah. Okay. Perfect. Okay. Sorry, I didn't know that was happening. So, okay. So if we go back to let's read me, we install the AWS CLI, we configure it, And then the next step is to run this Ceph4GW command. So if you want to have a look at that yourselves, again, you can open this up. Yeah, you can go through it there. And for the purpose of the demo as well, it's a vanilla install, so that I have no configurations for Vim or any other environment. Anyway, let's readme Ceph4GW. Let's go ahead and run that. So if you did have a running instance of here, that will stop it. So now, again, similar step as we had for hair HCTL. Part of this script runs the hair process of CORTX Motr, because remember, and for some of you, this topic might be abstract. You have CORTX Motr as the core. You have hair that helps manage it. Once you spin those two pieces up, the next step is to spin up the S3. So again, very similar to what we saw in the earlier step. We say, look, let's start the console server, update the configuration, and that goes through quite quickly. And that straight away jumps to the Ceph RGW, which uses CORTX Motr as the backend. So at this point, the shell output ran through quite quickly, but all it did there was run through the same setup we did before with hair and CORTX Motr, and also set up CORTX RGW. And in addition to that, actually ran some test commands. So if I scroll back on this input, I can see where I've left off. We start the console server. We can see, look, here's our HCTL status up output, this here. We create, within that script, everything related to Ceph RGW, and we can see, right, client, RGW backend store, we can see it's running Motr in the back. Again, running on port 8000, sets everything up for Ceph. Some additional things, some of you familiar with S3 and the configurations, this will look familiar to you. Max buckets, sub buckets, keys like this, etc. I won't cover it in this talk, but yeah. And the next part of running Ceph4GW is running these example commands. So in theory, we should now be able to take this command and it should return us an output, because this is going to be use AWS S3 on the command line to copy foo.txt into a test bucket where foo.txt is going to be object one. Okay, so all we do, this script, it just goes through an example of copying files into buckets, creating buckets, and deleting buckets, right? And the script then cleans up after itself. But if we were to take an example output without doing anything else, right? Without you going into AWS S3 CLI documentation and looking how to do this, you can simply just copy one of these commands and run them on your shell. So it should work. So let me see if that works okay. So here I'm saying AWS S3 is the protocol that I'm going to use, AWS being the package we have. I'm going to list the contents of S3 test bucket, and error occurred. And obviously this is totally expected because there's no such bucket when we call that. So let's try another one. Let's we can try actually, and before we try that command, there is a final command that we had. So if you recall, we ran Ceph4GW shell script, but we can also run the S3 AWS test script ourselves. So if we want to do that again, by all means we can do that. You can see again, we have a running instance of it, and we test against it. So, okay, I'm at 10:51, so we've got still a couple more minutes. If I want to quickly double check inside the processes, right? I can grep, so I can see Motr is there. I can see Ceph. We'll have some instances of that. So that's the setup. So everybody who's following along should be at this step where they can set up CORTX in single node with an S3 layer on top, and they can run these commands where they can create buckets, copy files into it, and then delete it as well. Yeah, that's kind of it for the setup stage. So I'll open up maybe to some more questions, or if not, yeah.
David, there's a question from Buket online.
Mm-hmm.
Could you write to S3 command here?
Could we do it live? is the question?
Could you just show the command for AWS S3LS for testing?
Yes, yes. So what we use for testing is this. We just run this simple script. So we can, this is just some simple bash commands. So if we were to run this now, for example, I can make this bucket. So that's, Buket, if that's what you mean by running the AWS command on the shell right now.
Yes, thank you. Yes.
Yeah. So here we just ran the command make the bucket. We had some previous ones where we list them. That's listing inside the bucket, right? But again, very quickly actually, we'll do something like this. It'll be easier to show side by side with things. So I'll get tmux up and running. Let's run that. So we'll split that, right? Can everybody see that okay? Yeah. So we can say, look, you can do that yourself as well. Get it, split it, make the bucket, list everything inside of AWS S3. So if I go ahead here and list this, it should say, so if you remember in the previous command, I went ahead, AWS S3, make the bucket, then list it, and we can see after we list it, we can see test bucket is present. Again, all of these, 1 second, I'll close this down. All of these commands can be found on S3 AWS as well. Right, so this is via command line. So via command line, you have an instance of AWS, but what you can also do is, for example, some of my own Python examples that I have. And you can simply use Python as well. So you could use something like Python with Boto3 package, and this will allow you to use the AWS, use the same commands, except you're going to be controlling creating buckets, listing files via Python as opposed to command line. So yeah, I think that's kind of it for the setup page.
I have one other question, rather unrelated to the whole setting up. I wanted to see if you wanted to also support next versions of, let's say, Rocky Linux, because as I was testing, I think in Rocky Linux 9, some of these packages like Power Tools have been renamed to something else, and this build setup is not working correctly. There requires some kind of modifications. But in Rocky Linux 8, of course, it works perfectly. I want to see if you want to support maybe in the future Rocky Linux 9, or you want to stick with Rocky Linux 8.
Yeah, Connection will move to 9 eventually, supported. Yeah. So for those online and didn't hear that, the plan is to move to 9 and support it. There's a little bit of work involved because at the minute this is tested on 8.6. So yeah, like you said, if there's some undefined behavior, it's because we haven't tried it out on that. But the plan is to do so.
Okay, thanks a lot.
Okay, no problem.
There's also a question from one question online, David, from Katie. So Katie says, how long should the HCTL start command take? It's been running nearly 10 minutes, she says.
HCTL start command, I assume?
HCTL start, yeah.
Yeah, HCTL start should take, this machine that I'm running is, it's quite modest. It's maybe 4 CPUs. So if within maybe, about a minute, if you don't see something happening, do try and investigate and see maybe in the processes, if processes are being spawned or killed off. And if it's taken more than a minute, something is probably not right or not working. So Katie, maybe even, or for anybody else, maybe reach out to my email because this is useful for us. If people are seeing interesting edge cases or things not working, this is something that we can use to fix in the future as well.
Okay, yeah, I'll send you an email about it.
Perfect.
Thank you.
Could you remind me which email you prefer to be reached at?
It's my first name dot last name at seagate.com. So David, like so.
Thanks.
Okay, so I guess we're at time, 10:59. So yeah, I'll go ahead and stop sharing there. Yeah. Okay. So, yeah. So the first step is setting up is done. Right. We finished that, and the next part is sample apps. So with sample apps, as we went through the CORTX repo setup, this repository here allows us to run motor client sample apps. So we went through the S3 layer that did it. Here we use CO, C0 copy, cat, and ORM commands. So this allows us to play around with CORTX in another way, right? These are built using the CORTX Motr directly. Yeah, so this is the accessing directly. Yeah. Yeah, the two of us. So yeah, so the difference there between the last demo and some of the commands that we had was everything was done through the S3 interface. But there's also another way to access and work with CORTX Motr is the direct API. So it's a little bit less user friendly in the sense that it's more low level, but it allows you to maybe get a little bit more performance or things like this. But all that aside, I think there is an example that we have for any of those interested inside of CORTX repo, a Go client as well that they can use using direct, but just for sample apps, we'll demonstrate it here. So moving in, so Seagate CORTX Motr app is what you're looking at, and then we're just going to simply follow the instructions. So here we can clone. If I go back to my command line, so let me see where I am. I'm in my home directory. I'm just going to run this command, clone it. Okay, so if we check HTTL status, okay, so everything's running. So we probably want to just sudo cl. So we just resort to the sudo pkill, right? Yeah, let's do that. So first one, M0D, isn't it? Yeah. Next one is hacks. That's it, I think. Rados gateway. Yeah. Yeah, like so. So that should have stopped, right? So once we clone that down, we cd, and then we run the autogen. So this is a good use case. Auto reconf is not present. Okay. So in this case, Ganeshan, what do you think move next? Mm-hmm. So yeah, so for 8.6, sample apps might not be just out of the box for now. Yeah, which is also fine as well, right? All it's doing, yeah, with this one package that it's missing, this auto reconf, like you said, it's a very good point made by somebody saying that version 9 is not, supported exactly. So exact same thing that we have, right? Because eventually we move from CentOS 7.9, yeah, CentOS 7.9, some of the earlier versions, and we have to be careful about which way we package these, right? So for the purpose, and again, sample apps, all they do, just to try and show you, right, as far as live demos goes, this is as live as it gets. But all it does is uses Motr API directly, right? So all of these are written in C. So somebody would have to have a little bit more knowledge than just running it with Python, but it's very straightforward. They could go ahead and do that.
Yeah, David, this is Deepak here. You could do yum install autoconf to get auto reconf.
Okay, brilliant.
That should work. Yeah, I've sent it out to the chat. Yeah.
Yeah. Okay. So thank you for that.
Yeah.
Okay, so now that's done. Let's see if we can run the autogen. Okay, we're missing one more.
There is also autogen package you can install with yum.
Okay, so this one is going to be sudo install autogen. Yeah?
Yes, I think.
Brilliant. Thank you, Buket. Okay. Let's try this now. Third time lucky, I guess. Okay. AC local. So we're still missing a dependency. So
because I know that CentOS and Fedora has this development group. Sudo yum
Yeah. All one word?
Yeah, group install is one.
Yeah. All right, let's try that.
It's like a group install and development too.
Sorry, yeah. Yeah.
You could go for auto make, yum install auto make. That will give you AC local.
Okay, let's try that. Yeah, sorry, my bad. All right, so group list. Okay.
Yeah, and the development details. Title. So you have to put it in the codes. Yeah.
So
this guy's because yeah, that's the original Red Hat title. All right.
Okay, so it looks like so, right? Let's try that.
For the OVA file, I will send it to the email. It's going to take some time.
So Martin, you're gonna share an OVA with the participants that they can use? All right, okay.
3 gigabytes and everyone can download it, just double click and it should import it in your
Okay.
Oops.
So Ganesh, you know more of this, yeah? Yeah. So. Okay. Like so.
Install OpenSSL sudo yum install OpenSSL devel. I think it's the header. Yep, make.
All right. So you might run into this as well for 8.6 as the latest, right?
Do you want to try in sudo yum install these?
So this was a dependency change, wasn't it, from cast XML to GCC XML?
Split to make clean.
And
then start from the sorry.
Yeah, run the configure and then a make. It's missing libxml at this point now. Yeah. So is it a devel or? So this is the, yeah, this is
I think it should be libxml2-devel.
2-devel. Thank you. So let's do make clean. So at this point, probably that dependency.
We need to install this anyway.
Yeah.
Without installing it.
Yeah. Or is that something we want to skip, Ganesh? Maybe.
So Perl XML.
Mm-hmm.
Just copy that line.
Yeah.
Add.
Okay.
Fantastic.
All right. So everybody.
Yes.
Yeah.
See your copies, your gets, you are on the all there.
All right. So everybody who's following along, they probably would have had the exact same thing to untangle a couple of dependencies, right? Okay.
Try to make VMRCF.
And probably can refer back to here, right? So if we run make.
You will need to be quick.
Yeah.
Go down.
Yeah.
Yeah, these ones.
So everybody's who's here. So we ran make at this point, and then the next one is make VM or CF, right?
Just to generate sockets. Yes.
Okay.
And test. This is because I think the process is not killed correctly.
So if we say pkill, right? Whoever was doing the same didn't get the chance. Sudo pkill. Yeah, or we just do M0D.
No, if you kill it now, it will kill the cluster.
Yeah, or we just double check sudo shutdown HCTL is what we need. This should be fairly quick, right? Exactly what we talked about. If you have a running instance and you try and run these tests, those tests won't work, right?
Yeah. So create the disk drives again.
Yeah.
Okay.
Should that, for the people who are following along, should the make work okay, or do we need to start?
VMRCF and then make test.
It should work out of the box without the disks being created, right? Okay, so maybe we try that, but just to double check again, what we show there is if you try and attempt to run these while the cluster is running, you'll get this error. So just double check sudo HCTL status, cluster is not running. Okay, so this is where we want to be before we run it, right? So we said make is what we try and run.
Now we need to create a cluster. The cluster is not running.
Mm-hmm.
So start the cluster.
So will I go ahead and make this command then? No, okay.
Just cluster need to be run.
Exactly like we ran before, right?
Yep. Cluster.
So same as we had, MKFS single node in here. So let's start this up. Yeah, and just referring back to the question, how long it takes, roughly, like I said, on a 4 CPU machine, 101722. By the time we get 101747, we start motor, phase 2, MKFS. It's about a minute or so. Yeah, 1055. Yep. Yeah. CORTX Motr VM, yeah. Or sorry, sample apps.
Control status.
Mm-hmm. Okay. Cluster is running, yeah. Mm-hmm.
This is because of the earlier problem. We are trying to use the same machine for running the S3 interface and also the sample apps.
So maybe if
I will demonstrate on my machine. I'll share my machine.
Okay. If you want to go ahead and if you have that prepared. Okay. And that's going to have a running cluster and the bits there. Okay. Let's try that. Yep. So I'll go ahead and stop sharing and I'll let Ganesh show an example of motor apps where S3 isn't running. Okay. I just have to get access to that. Maybe if I stop sharing, if that's okay, and maybe we share that with Katerina. Yeah. Yeah.
So can you all hear me now? Okay, I'm starting the cluster. So this is exactly the same cluster, but this time I'm not using the S3 interface. Okay. Okay, as you can see, the cluster is running now. So here I got the some labs. Let me do make clean. So Meg should compile all the files without any problem. So now that the cluster is running, so I can call VM RCF to create the sockets. So that's creating all the sockets for all the applications. Make test should work now. Yep, as you can see, it's working now. The first one is deleting the objects, and then it is doing some copy and then some cat. As you can see, it outputs some statistics, performance details as well. It copies a file and then read it back and then compare the file. So it just compares file 1 and file 2. And if there are any errors, it says the files are different. As you can see, it gets back the same data. And then finally, the objects are removed. So using the CORM command. So this is basically a demo of using the direct access of CORTX Motr API. Any question? If you have the VM set up properly and all the dependencies installed, it should work out of the box. Exactly. Yeah. I mean, the first time when you set up, you need to install all the dependencies. Yeah.
Yeah, exactly like we said, so this is, we have the instructions and it goes through, but it's good to show and walk through together, for example, of what might happen where you're missing a dependency, you can't install it, you try to get it back on the machine, and you said, yeah, there's a couple of moving parts, even just to get the cluster running. But for the most part, it should be straightforward. But there is a certain amount of learning to have when you're setting these systems up. Anything else that we'd like to show, Ganesh, for this? So this is direct
so I can
access.
add one more thing here, that if you look at the commands, for example, this is the CO copy command, and then I have got two numbers here. So this is the 128-bit object ID. If you're going to write your own program, then this is another problem, that you need to manage the object IDs by yourself. So in my case, it's a simple program, copy and CAD. So I have this fgen. It just gives me two random numbers, just to make sure these numbers are not regenerated. I mean, it's a unique number every time it generates. Similarly, I mean, if you're going to write it, use it for your programs, you need to have a way of managing the object IDs.
Yeah, so I think that's the 2 points mentioned, right?
Yep.
So over the last hour, we showed how to set up a single node cluster running S3, and also test out the sample apps that do motor direct access, right? Yeah, the other thing I mentioned was we do have an example of using motor direct API using there's an example application using
so we can go through one of the CO copy or CO CAD programs if you like.
Do you want to? We still have 5 minutes in this section. Do you want to maybe?
Okay.
Run through
So
it
let
quickly?
me. Yep. Okay. Let me stop sharing this and then go to the repository. Okay, so let me share the sample labs repo. So let's have a look at this program here, CORM. So this one simply removes or deletes an object. So if you want to write your own C program, as you can see, you will need to have two 64-bit IDs. So because the object ID is 128-bit, you need to have two of them. And then you will do some initial setup. Okay. Okay, so here we have this function, COABS remove, and you pass two IDs, and then it just removes that object. If the object is already there, it gives you a number as the output. If the object is not there, it will give you another number. If there is some other error, it will give you another integer as the error. So you just need to manage those error messages according to that. Otherwise, it's just a matter of calling this function. Similarly, if you look at your copy, you will have COABS copy, and then the file name that you are copying into, and the ID high and ID low, and then the number of blocks you want to use for copying that into motor objects. So just like this, this is delete. You can replace this delete with copy cat, and you can build your program using this as a skeleton. Any questions? Do we want to go through another example?
Is there an explicit blocking?
Sorry.
Yes, sorry, I forgot to use the microphone. So my question was whether there is a way how to obtain an explicit lock on an object.
So this direct access is basically you are accessing as you are requesting it. So you just need to manage at the higher level if you want to preserve data and all that. Once you have the ID, object ID, you have all the power to access it and modify the data at the lower levels. So this API is like that. It's a very powerful tool.
So if I'm, for example, if I request the delete of an object, and immediately after that I will call read or write or something like this, it will fail the call.
It will be deleted. You will lose the reference immediately.
Yeah, so I think we're at time. So the next section is ephemeral services. So Ganeshan, if you want to stop sharing, I'll go ahead and
Okay.
I can stick with this mic.
Let me stop.
Yeah. See that? Yeah, coming through okay.
Yeah, all good, David.
Yeah, so I'll just switch over to this mic here. So we talked about the ephemeral services and the IO-SEA stack now at this point. But what I'd like to focus on, and this is an example that Philippe Cuvet gave a really good presentation on October 13 at IT4I. So I'm going to be touching up on the same points and just maybe talking a little bit more with CORTX Motr with context. So what we're focusing on here is the image that you see in front, right? Long-term storage, HSM. In this case, we're going to be looking at everything to do with ephemeral services. So like talked about before, and it was a really good presentation. I urge anybody who's watching now and didn't see that one to look at that one. Is everything to do with the data nodes, them being close to the compute nodes, how we are assigning, how we're creating workflows, how we're assigning resources to these data nodes, and how we have different clients that are running on these data nodes that are then going to contact the long-term HSM. So yeah, that's kind of an overview. We'll only be sticking with ephemeral services. So I'd like to contrast what are ephemeral services, I suppose. What is the definition in the IO-SEA sense? So we can contrast that to the standard IO service as a perpetual resource. Maybe it's a one-off storage resource that's created. Multiple clients are using it. We might run into situations where we get too much usage out of it, and that resource cannot just simply cannot handle it, right? So in this case, they wouldn't be dedicated to a compute job. So an ephemeral service is, you can kind of closely think about it as a workflow or an abstract model in your head. As each compute job starts, the associated IO service dedicated to compute job will be started on the data nodes, right? So compute uses a dedicated service, and in this case, instead of the perpetual service, it doesn't impact the global storage servers. And again, if we remember back the MSA architecture, where that's the presentation that Sai gave, all these ephemeral services run on the data nodes, and they're close to the compute nodes, and can be thought of that the life cycle is linked to a compute job. When we say keystone part of the solution, it means that for all other workflows like DASI, some of the others as well, logging, it is important to have these ephemeral services up and running. So next step. So where CORTX comes into IO-SEA is that CORTX is great scaling as an object store, and it meets the requirements that IO-SEA needs. The only thing is that those objects are stored in a flat namespace. So if you can think of a scientific experiment or any other data, two objects won't have any connection and they'll be independent. So we store the data without any organization. But data organization is very important. If we can think of some of the use cases that Sai presented, for example, the weather, some of the astrophysics examples, data created in step 1, step 2, and any other subsequent step, they might need to be accessed and created together. So where simulations, where the pieces of data explicitly depend on each other. So for this point, we have the definition of data sets and namespaces. So again, this is a concept we went through multiple times now, but it provides a way, an organization on top of the object store, which we otherwise wouldn't have. So what is a data set? A data set is simply a way to group pieces of data that have reasons to stay together or be used together. And namespaces are the way the data is seen by the end users. So a namespace might be accessed by S3 POSIX interface, and it's always built on top of a data set. So in a way, it exposes to the users an organized view of the data inside the data set. And kind of within the work packages, this is the only feature which deals with these concepts. So referencing back from the previous slides as well, here's a more of a graphical representation where a data set, we store it as one S3 bucket. And yeah, the files can be stored as S3 objects. And namespaces, again, storing metadata with the objects. So yeah, a good example, as shown, think of it as a set of directories and symbolic links to objects in the data set. So hopefully this topic is quite clear. Sai gave a great introduction to it. Before that, Philippe Couvet had a great presentation. So I hope now at this point, it's quite clear what a data set and namespace is in the IO-SEA project. So covered in the previous talk, which I won't go over this time, there's the idea of workflows, which make use of ephemeral services. It's great that we have ephemeral services, but what's driving them? What's using them? And it's the workflows and the workflow definition files that will be able to be created and to be around those workflows. So very briefly, data sets, namespaces, a way to access those namespaces, which I'll show in the next slide, and ephemeral service types, right, that you can specify. And there's a whole other presentation that talks about that. So more of a graphical view. On the left side of the screen, you can see the different clients that will be running on the compute nodes. You can see we might have instances of an SBB client, an NFS client, S3, DAISY, and some of the others. And within the data node, we will have a motor server and a CORTX S3 interface. So similar how we set up a single node CORTX Motr with S3 running, and we were able to execute those S3 commands. Something similar is going to happen within this data node, as you can see. So in the middle of the screen, you see the data node. CORTX S3 server refers to the Rados gateway piece as well. So long-term storage on the right, you can see that storage will be attached to the motor server, and then the instance of the motor server set up on the data node itself will be able to talk to the long-term storage. And again, if you remember or attended some of the talks with what's the role of HSM within long-term storage, data node, and the ephemeral services. So for CORTX as well, right, it's quite flexible in the way, and that's why we wanted to show you this Motor Direct Access API and also the S3 to show you that there's not just one way of using CORTX. Say, look, you have to use S3 and that's it, that's the end. You are free to completely use CORTX in any way you want. So in the architecture of IO-SEA, where the data node will have motor server and a CORTX S3 server on top, and then some of the clients which would access it through an NFS client or an S3 client, will also be free to, if we need to use Motor API directly, if we want to. So we could build another layer on top of the motor server, which might be CORTX, like we have CORTX S3 server now, but it could be something else if the application requires it, right? So if we need that access. One thing I will say is at the minute now, CORTX S3 server offers additional functionality, like we talked before. Some of the ACLs and some of the permissions, right? Motor API, it's great, it's performance direct, but but a lot of those layers have to be built on top yourself. So that's kind of it for ephemeral services. I know we talked about ephemeral services before, previous talk, and in the introduction. Yeah, Sai's introduction was good because he went over this as well. But yeah, that's what I wanted to cover in this talk, just to show you hands-on and see, because it's very easy to show this diagram and say, look, Motr server just works as it is, without having a concept of where does the S3 live and how do the commands get executed. So I hope this gives a better understanding to how we deploy CORTX within these data nodes for the purpose of ephemeral services. Yeah, and that's it for the ephemeral services piece. Yeah, so finished a bit early. Suppose any questions as well? Maybe we want to open up the floor to that.
There are no questions online. I'm not sure if in the room somebody wants to.
David, one thing that might be relevant is just what's the latest that's happening in IO-SEA? What's been done from a CORTX Motr perspective for ephemeral services? Maybe a quick status update might be relevant, I think.
Yeah, so that's a good point. Thanks for that, Si. So at the minute, at IT4I, we have an OpenStack cluster, and we have CORTX Motr deployed as part of that. We're working towards more of a multi-node setup now as well. So the idea is, as we have the prototype of IO-SEA running along with some other ephemeral services, CORTX is now running a single node, a couple of other nodes, but the idea is to scale that up. So as we begin prototyping more and more on the experimental IT4I infrastructure for the IO-SEA project, we'll be moving towards that side. So we'll be deploying more and more instances of the S3 and Motr. So try and scale it up as we continue on.
Thanks, David.
So if there are no other questions, we can maybe prepone the lunch break. I'm not sure if we want to keep it 1 hour, which means that we would come back at 12:45.
Is that okay?
Yeah.
There will be an afternoon hands-on session and then closing. So I would say that we enjoy your lunch, and we will see you back at 12:45.
Yeah. Thank you, Karina. Yeah. See you all in the next 1 hour.
Thank
Have
you.
a nice lunch.
Yeah, so welcome back to everyone that's joined us for the last session. So in this session, we'd like to go over the setup that you have, or any issues that you, excuse me, any issues that you may have with your installation. So it could be something simple as the cluster not starting up, not shutting down. There's a couple of moving parts. So myself and Ganesh will be assisting anybody either via chat or some of the people in the room who are trying to set up. It could be a dependency issue that you're trying to pull in. So this session is really for participants who are testing things out on their installation. So yeah, Ganesh as well, just to get your input on this one. I think this one's more of a free session as opposed to a structured presentation.
Yes, yeah. Yes, David. Yeah, just to motivate this session, it's supposed to be a session where we would like everyone to try out some of the things that David and Ganeshan went through in the morning, and Ganeshan and David, they're on site to help out with any issues that you may face. So yeah, it doesn't have a definite structure, but yeah, I mean, we are also there to yeah, take any questions that you may have when you play with this play with the setup, right?
Yeah, so if anybody wants to open up with questions, or suppose we'll stay on standby for the time being, or do we?
Yeah, and is there a set of, is there any like instructions that they which is documented somewhere, David, or can they just go through like any setup videos or something?
Yes, so if I just briefly share my screen there. Yeah, you can see that okay? Yeah, you can. So between CORTX Motr VM sample apps. So in the previous session, we covered where we have direct CORTX Motr API access, and also trying out the, sorry, it was this one, apologies. This was the CORTX Motr sample apps that we had for people to try out using the direct API, and also this CORTX Motr VM. So in here, in the VMs, as we had before, they can set up Rocky Linux, right? And also test out the commands themselves. So Sai, I would recommend for anybody to test this out themselves. As a first step, once they have it running, is to open up S3 AWS shell command and simply have a look at the individual commands like listing buckets, creating a text file, putting that text file into a bucket, deleting it, simple things like this. And then they can possibly move on to maybe testing that out with Python example, right? So that allows them programmatically to maybe create 10 buckets, delete 10 buckets, maybe take a corpus text and do a word count. So you might have a 2 or 3 megabyte file that has 50, 60,000 lines. You might say, look, how many instances of a specific string do I find? Things like this, you know. But the first step would be to look at this AWS test commands.
Do you want to paste the link on the chat? Maybe David, would that be yeah, on the Zoom chat?
Yeah, 1 second. Yep.
Perfect. Yep.
And then I will also go ahead and take this S3 AWS shell command. So here, for example, on so this is another link. This is the S3 AWS shell command, starting line 24. So very briefly, what I shared there on screen is this file here, which we ran in the first session, setting up CORTX Motr VM, is the 10:30 to 11 session. So here they can take these commands and test it out themselves. And for whoever is not familiar with even command line AWS, simple things like you might, so I'm logged in. You might have a look and make sure your credentials are okay within this AWS credentials that one script creates. So to some of you who are working away through getting the setup, installing dependencies, I put 2 files in the chat. It's a Python example. So quickly run through. So same as we had before. Some of you might have completed the AWS CLI, so you could use that on the command line. It's a very, very simple Python script that allows you to list buckets, create buckets, delete a bucket, and just a simple driving main function that allows you to do that, right? So it automatically picks up the AWS credentials that are stored under home /.aws/credential. So you should be able to run that. But before that, if you're familiar with Python and virtual environments, if you're not, just use cat on. Sorry, I just moved this down. Use cat to show this. So if I follow the example, cat readme, let's say, just prepend that Python. The very first line where it says Python -m, I have that alias to my system to go to Python 3. That's usually a same default. So VNV, I already have that. But anyway, we're going to source it, virtual environment. So any packages that we create within this session that we have created, it's only going to be within this folder rather than messing up all your global system, right? We activate it, pip install Photo3. So I have that dependency already installed. Yours will install it. And it's as simple as one Python example. Sorry about that. Zoom banner sticking around. Then we run it. So very quickly, we just say, look, we found the credentials in shared credential file, exactly like I said. Very simple log message that we completed the init. We list the buckets. So this is a pretty print here. We show the existing buckets non-exist. Create a bucket. Test bucket's been created. We list it. That's just a standard Python print. More of a pretty print here. We delete the bucket and then we clean up. So we can kind of tack on to that. So if you have any existing Python scripts that do anything with this, both O3 and AWS command line, in theory, you should be able to just run this or your own script that's using AWS command line or both O3 in this case, and it should work. So if you're using this against AWS S3, it should also work here.